enjoyed the posters yesterday. So for the speakers, there's a 10-minute timer here. When it gets to 8, it's going to flash to amber. So that's your cue to wrap up. And we'll hopefully have some time for some questions at that point. You can ask questions either in the room, please come to the microphones, or online on the app. We're keeping an eye on that as well. So to start with, we'll start with Lance Bozart on the contributions of subsidence and horizontal advection to the Western European heat waves of 2022.
Thank you, and good morning. Time permit does not permit talking about both the June and July, so we'll just focus on the July one. I want to acknowledge my 2 PhD students, Tyler Light and Alex Mitchell, without whose contributions this talk doesn't happen, and the NSF for making it possible for me and my students to conduct curiosity-driven research. All right. The motivation here is the record-breaking July heat wave scorched Western Europe, really remarkable, with all-time heat records set in the UK. But it didn't occur in the usual way. And I assumed that it would occur to the effect of Saharan air reaching the UK, but that was wrong. So purpose want to show how an Eastern Atlantic cutoff cyclone fostered a Western European region, which led to the heat wave. And we'll look at some other things along the way to support that. All right, so first of all, overview of the Western European heat wave and temperature records. So that's a map of the extreme maximum temperatures between the 17th and the 23rd of July. And the deep reds are 35, 40, and 45 C. So it's just a little bit toasty in that area. And this is a remarkable figure. In the UK, July 19th was the hottest day on record in the UK ever. And you can see there's the time series of the records. So in recent years, there have been records that have been broken, and they continue to be broken. But the records were broken by large amounts. In degrees C, the width of those lines mostly is in the range of 3 to 3.5 to 4 C, and the biggest leap is 6.3 C. When you break a record in an area that's had more than 100 years of records, and you break it by 3 or 4 degrees C, you're talking something that's maybe out of this planet. London on the left, 104 in London. That's just unbelievable. 40 C. Paris did not break the record, but you can see on the time series there to the right that the hottest day of the year was on the 19th. All right, so let's take first of all look at the large scale flow evolution during this 11-day period to see how things went. So I'm going to show you these maps that are once a day, starting with the 0Z on the 10th of July. The left panel in shaded is the jet stream at 250 millibars. The first shading interval is 30 meters per second. The solid lines are the sea level isobars. The dashed lines are the thickness pattern, changing from red to blue at 540 decameters. On the right panel is the 500 millibar heights and contours. Wind barbs are plotted, and the shaded in the orange to red colors are the vorticity and the scale on the bottom, and the blue areas represent areas of ascent. So the thing to notice at the outset here, this is the 10 days before the hottest day in the UK. There's a trough off the coast west of Spain, and the ridge over the UK. So those are going to be the players that are going to interact with one another as we go forward. So we go one day forward. The cutoff now is developing off of the Iberian Peninsula. So I want you to pay attention for the next several time periods to what that cutoff low does. It spins around. It looks like, it wants to visit North Africa. No, I want to go west. No, I want to go north. I want to keep going north. Now I want to go away from Spain. And now we're up to the 16th of July in there. But meanwhile, the main flow pattern is across the North Atlantic Ocean further to the north. And so there's no direct ridge from North Africa. But now we come back to the 17th. The glow is coming back towards Spain, in through there. And note what happens in the next 24 hours to 48 hours as the low cutoff low moves back towards Spain, the ridge builds to the north. Note that the partial ridge building is conjunction with the westerlies across the Atlantic and the ridge building ahead of the cutoff cyclone. And then 0Z on the 20th, the low cutoff cyclone finally opens up, but now you have a ridge that's moving eastward. So the heat wave, hottest day, hottest weather, while extreme, was relatively short-lived. So where did the air come from? So if you do a high split trajectory analysis, 168-hour backward trajectory analysis, for Paris left and London right, what do you see? No air coming from the Sahara in through here. This is air coming that ends up at 500 meters above the ground. The dominant figure at the bottom shows that roughly 3,500 meters of descent. So this air is strongly subsiding as it comes in off the Atlantic, curves around, and then comes back in from the east into Paris on the left, and it comes in from the southeast and south into London on the right. So one of the things to look at, we can calculate what the temperature tendency due to horizontal advection and vertical motion was in these two boxed areas. So we did the cutoff cyclone averaging areas in red, and the London-Paris averaging area is in blue, and the averaging period is over the 10 to 22 July every 6 hours, and the data set is the ERA 45 analysis. So this is a 700 millibar temperature tendency calculated by the equation in the upper left corner of the screen. The temperature tendency at 700 is the blue line. Due to horizontal temperature tendency is the red line, and the green is the vertical temperature tendency. And this is in the cutoff low, and the two vertical purple lines are the period of the hottest weather, hottest in the UK and in northern France. And the thing that you see that dominates the temperature tendency in the cutoff low is the vertical temperature tendency, that pretty close to the total temperature tendency in through here. Now, if we look instead in London and Paris area in there, we see a different signal in there. Leading up to the heat wave, the vertical temperature tendency warming due to subsidence dominating there, working with warming due to horizontal advection as well comes in. But around the 18th, where you have the red dominates, that's the horizontal temperature tendency advection as the vertical temperature tendency weakens in there. And during the actual hottest part of the period in through here, it actually suggests cooling. But see, that's misleading, because what's really going on is the subsidence below 700 millibars, which the trajectories allow you to see. So the takeaways in through here would be that, and the cutoff cyclone is primarily driven by weak, less than ½ degree C for 6 hours, warm air advection during 12 to 15 July, and by subsidence warming in the period 18 to 20 July. And the London-Paris is driven by subsidence warming of over 1 degree C for 6 hours between the 15th and 18th in July, then a bit of cooling due to horizontal advection on the 19th of July. So the conclusions that come up and through here is that extended high latitude upper level ridging across northwestern Europe favored a prolonged heat wave, but it turned out not to be prolonged, but it looked like it was going to be prolonged initially. Southerly flow east of a persistent cutoff cyclone west of the Iberian Peninsula contributed to upper level ridging over Western Europe, whereas subsidence warming at 700 hectopascal in 18-19 July weakens the cutoff cyclone west of the Iberian Peninsula. And the London-Paris back trajectory show that subsidence, roughly 3 kilometers, drives warming in the 48-hour period. So lots of different ways to get a heat wave. I would have bet good money that if you get that hot in London, you got Saharan air that somehow got from advected northward, but that's not what happened. And since I have just a little bit of time left, I can show you it's an additional high resolution slide showing the strong subsidence in the last period from right into London in there. But here are the time mean in there, the mean and anomaly geopotential heights. And you can see on the right panel in the red, there's a huge anomalous anticyclone. It's not really anomalous. No, the 500 millibar heights are not anomalous. 300 millibar heights are not anomalous over Northwest Africa. And to the last slide here, if you look at the 850 millibar mean and anomaly right, what you see over Northwest Africa is slightly cooler. Less hot. It's not hot. It's always very hot, but it's less hot. But the real warmth is clustered over France and Northwestern Europe, and it's subsidence driven, which to me surprised me in terms of, I've been looking at close to Avogadro's number of weather maps in my career, but it's nice to know you can still be surprised by something you see that you hadn't thought could be possible. Thank you.
Thanks, Lance. That was awesome. Why was this apparently never has happened before? It was given the magnitude of the records. So what is this? Why was this so unique? Was this subsidence lasted really long time? Was it really strong?
No, it did not last a long time. The hottest days were like 2 to 3 days.
Yeah.
Because the cutoff low came in and the ridge built then to the east. And there's a story for another day here. That ridge that built into the east moved eastward in discrete steps and actually is linked to the Pakistan flooding that occurred in August. But that's a story I'll tell at AMS.
It's like,
Based on this analysis, would you say that in general, these substance-driven heat waves got potential for more intense heat waves than the more advective-driven ones from the Sahara?
That's a good question. And I've thought about that. And I don't know, because this is the first time I've seen such a strong, in this part of the world, such a strong substance-driven heat wave. But that's a very good question. That would be very a project well worth doing, especially in a changing and warming climate.
And as a follow-up, do you think if it had been more longer lived, if that substance-driven warming had been sustained, do you think the heat wave could have been even more intense?
Yeah. But it's hard to imagine a more intense one than what occurred. I mean, most places there don't have air conditioning. So, I mean, that was a serious 40C in London, you know. Big Ben didn't like it.
Can I just make a quick comment? I mean, my garden was pretty dried out by the end of the summer this year. So I wonder if it's possible that there's some soil moisture feedback going on here as well.
Absolutely. Yeah, surface-based mixed layers halfway to Mars. You don't expect to see that in the UK.
All right, thanks very much. So our next speaker is Yi Zhang about an upper bound for extreme temperatures over mid-latitude land.
Okay. Thanks. And I'm very happy to share my recent research in collaboration with Bill Booth. So a major concern for climate change is that extreme events could get more extreme. And an example is that extreme temperatures over mid-latitude land regions have been increasing about twice as fast as the global mean surface temperature. And in the past few years, we have witnessed a few extreme heat waves that have broken previous long-standing temperature records. All these phenomena led us to ask the question, what controls the maximum surface temperature over mid-latitude land? There are many studies focusing on the drivers of heat waves. And simply speaking, blocking anticyclones associated with some soil moisture feedback could raise the surface temperature very rapidly. However, in order to know what controls the maximum surface temperature, we need to know what determines this turning point. And this will be the focus of this talk. So first, we noticed that there's a precipitation surge right after the surface temperature reaches its local maximum for many regions over mid-latitude land. And here I am showing an average time series surrounding the annual hottest days and averaged for all locations and all the years. And this observation inspired us to make the hypothesis that convective instability is associated with the decline of the surface temperature after it peaks. So surface temperature cannot rise indefinitely, but at some point, the column will become neutral and marginally unstable to convection, and therefore it produces rainfall and cools the surface. So to derive an upper bound for surface temperature, we adopt a very simple criterion for convective stability, which is that the surface moist static energy should not exceed the saturation moist static energy in the free troposphere we take as the 500 hectopascal level. And the reanalysis data is consistent with this hypothesis. Overall, the surface moist static energy is lower than the free tropospheric saturation MSE, but these two only meet on the hottest day. So we expand the moist static energy into its three components of temperature, humidity, and height. And the right-hand side can be approximated as a function of T500 only. And for the left-hand side, if we let the humidity to go to 0, we allows all the available moist static energy to be allocated to surface temperature. And please note that the ZS term is constant and is considered a known property. So then we are left with a theoretical upper bound for the surface temperature, which is a function of just T500 alone. And now I plot this upper bound in the phase space of TS versus T500. And this is what it looks like. We can also plot all the data points from all over the mid-latitude land in this figure, and this is what distribution looks like. So consistent with our expectation, there are very few data points exceeding this upper bound. And though this upper bound is based on a very simple idea, it is quite effective in explaining the patterns of the data. So for an atmospheric column to go from state A to state B, we first need a stronger anticyclone, and that would induce higher T500. And in the absence of any other changes, the temperature would be raised to A prime. And then some surface moistening could lower the actual temperature to B. And of course, we can have a higher T500, but also a drier surface condition, which would lead us to a higher surface temperature denoted by C. So what happened during the Pacific Northwest heat wave? On the right, I'm only showing the data points over this region, and the climatologies are in gray. The climatological distribution is below the upper bound, and that is because this region is never completely dry, and therefore the upper bound should be understood as a scaling. And the new temperature record set by this heat wave is indicated by the red dots, and the previous record in blue. There is a 5 Kelvin difference between these two records. So you can see that the motion from the blue to the red is mostly parallel to the upper bound, and that suggests surface conditions played a minor role in this case, and T500 should play a major role. And we can make this point quantitative by taking a derivative of our theoretical upper bound. So we have DTS, DT500 on the left, and the magnitudes of 3 terms listed. And I want to draw your attention to the second term, which is a Clausius-Clapeyron term. And it can vary a lot depending on which T500 we started from. In this case, it's a heat wave. We started from a rather high T500 and adding another about 2 Kelvin of anomaly. The Clausius-Clapeyron term contributes almost the same as the T500 alone, and plus a small contribution from the geopotential term. The anomaly at T500 is immediately doubled at the surface. So with a 2 Kelvin of anomaly at 500 hectopascal level, the surface temperature could increase by 4.5 Kelvin, which almost explained all the 5 Kelvin temperature anomaly of this event. And coming back to the question of the trends of annual maximum temperatures over land, we can do the same calculation, but this time we take a different T500, which is a typical value for the annual hottest days over all mid-latitude land regions. And then we get, for 1 Kelvin of temperature, a T500 anomaly, we get a 2 Kelvin increase in the surface, in the upper bound of surface temperature. And if there's no change in surface humidity on the annual hottest days, then we would expect that the actual annual maximum temperatures also increase by 2 Kelvin with 1 Kelvin of increase in T500. And the T500 has happened to be increasing at a similar rate as the global mean surface temperature. So the annual hottest temperatures appear to be increasing twice as fast as the global mean surface temperature. So to summarize, we propose the idea that convective instability halts the development of heat waves. And based on this hypothesis, we provided a theory for the upper bound of mid-latitude extreme temperatures near the surface. And this can be applied to individual heat waves or the overall trends of annual maximum temperatures. Thanks, and I'm very happy to take any questions.
Do you have any questions?
This is great. Just wondering, in this framework, do you consider the influence of the convective inhibition? Because typical sounding that could be found in the real world, for example, the central United States, is when the sun is already unstable, but there is strong inversion near the surface. In that case, the temperature can still increase until the near surface inversion is removed.
Yeah, thanks. That's a great question. So in the presence of CAPE and in the presence of convective inhibition, CAPE can accumulate, and that would deviate the vertical temperature profile from what I assume here, which is a perfect Moishe-Debat. So we can do an estimation of how much it affects our solution. So a typical CAPE value is about 1,000 joules per kilogram, and if we divide it by the heat capacity of dry air, CP, which is also around 1,000, then we get about order of magnitude 1 Kelvin of deviation of temperature. So that is the error could be caused by convective inhibition or CAPE.
Yep, one more.
Okay. Yeah, nice talk. Do I interpret your last result as saying that continental drying really hasn't been an important driver of the increase in extreme temperatures over mid-latitudes?
Sorry, did you say continental drying?
Yeah.
Yeah, I was saying that the continental drying is not playing a big role. And the drying is in a sense of specific humidity, not relative humidity. So I'm saying that specific humidity on the annual hottest days are not significantly changing for reasons that's not totally clear now.
All right, thank you very much. So our next talk is a virtual talk by Jiakan Yuan on linkages between amplified quasi-stationary waves and humid heat extremes in Northern Hemisphere mid-latitude.
Hello, everyone. I'm Jiakan Yuan from Fudan University. I'm very glad to be here and share a recent work of my research group. A striking feature of recent heat waves is that extreme heat has occurred simultaneously in several parts of the world. Some studies have suggested that quasi-stationary waves may play an important role. As the phase speed of quasi-stationary waves is close to zero, they can provide persistent conditions that favor particular weather at certain locations and further favor the occurrence of weather extremes. Our previous study found that by the end of this century, high amplitude quasi-stationary waves at wave number 2 can explain over 30% increase in frequency of dry spell days in United States and Mexico, and can explain over 30% increase in frequency of heavy rainfall days in South Asia, Indo-Chinese Peninsula, and South China. Como et al. Defined an index called mid-latitudinal extreme, high positive values of which denote extremes occurring simultaneously in many locations. They found that high amplitude quasi-stationary waves at wave numbers of 5 to 8 favor occurrence of high temperature extremes at multiple locations over mid-latitudes. Besides high temperature, high humidity is also important regarding the heat damage to human health. In hot environments, human body can dissipate 75% of body heat via sweat evaporation. High humidity can suppress the spread evaporation and induce abnormally high body core temperature, then cause heat damages. So humid heat extremes are very dangerous. However, it's still unclear what are the key characteristics of quantization waves linked to humid heat extremes. Are they different from those linked to high temperature extremes? And what are the mechanisms behind them? To measure the humid heat condition, we use the variable Webb temperature based on an isobaric Webb temperature approach, which calculates Webb temperature by solving the enthalpy balance equation at constant pressure. We extract amplitude of quantization waves by applying fast Fourier transform on monthly mean 300 hectopascal meridional wind over mid-latitudes. Here we show the wave intensity of wave amplitude for the first 10 wave numbers. It's clear that wave numbers of 5, 6, 7 have the largest wave amplitude among these. So we focus on the 3 wave numbers and pick the high amplitude amounts based on the time series of the 3 waves. Both horizontal and vertical structures of the composite meridional wind based on the high amplitude amounts show corresponding wave patterns for the 3 wave numbers, respectively, and are barotropic vertically. To ensure that the composite wave phase can represent the majority phases of individual months, we examined the phase lock behavior over the mid-latitude. Here we show the probability density of the phase position during high amplitude months. The distributions exhibit a roughly symmetric single peak for all 3 wave numbers, indicating that the associated southerly or northerly centers reoccur over a confined longitudinal range. Here we show the probability density of mid-latitude extreme index over length, well red for high amplitude months, black for other months. High amplitude months have more probabilities of positive values of max than the other months, as high positive max denotes humid heat extremes occurring simultaneously in many locations. This indicates high amplitude quantization waves prefers concurrent of humid heat extremes. Here we defined an index of extreme humid heat maximum duration, which is defined as the number of maximum consecutive extreme humid heat days within a month. This figure shows composite of this index based on the high amplitude months for the 3 wave numbers, respectively. Hatched areas are not statistically significant based on Monte Carlo and the field test. Amplified quantization waves favor prolonged humid heat extremes over certain regions. Say, North Central North America for amplified wave 5, Western United States, South Central Asia, and Eastern Asia for amplified wave 6, Western Europe and the Caspian Sea region for amplified wave 7. At the same time, we use blue lines to indicate areas where composite of high temperature extremes are statistically significant. Most areas where high amplified quantization waves influence the humid heat extremes are different from those for the high temperature extremes. To investigate the mechanisms of those key regions for each wave numbers, we have examined the dynamic and thermodynamic process related to the high amplitude station waves of these regions. We found that dominant mechanisms are alternative across regions. For instance, for the wave number 5, The prolonged humid heat extremes over the central North America is dominated by positive humidity anomalies that are induced by warm advection and moisture transport along the Great Plains low-level jet. We also examined the mechanisms for other regions in wave number 6 and wave number 7. Due to the time limitation, I just skip this and go to the key takeaways. In this study, we found that amplified quantization waves favor prolonged humid heat extremes over certain regions, as we listed here, and most of these regions are different from where amplified quantization waves influence the high temperature extremes. Mechanisms of the amplified quantization waves influencing prolonged humid heat extremes include anomalous horizontal winds increase near surface humidity by enhancing moisture transport and moisture flux convergence, increase the warm advection, increase the downward solar radiation, and adiabatic heating associated with anomalous descending motion, and increase latent heat fluxes from the surface. But dominant mechanisms are different between different regions. I'll stop here. If you're interested in this study, please find more details in our papers on Journal Climate. And we also published WBGT, Web of Globe Temperature Data calculated based on the isobaric approach on the Zenodo. It can be accessed through this code. And if you have any questions, please feel free to contact me. Thank you very much.
Okay, are we on the Zoom? Okay, are you there, Jiakan? Ah, excellent. Okay, do we have any questions? Somehow, maybe say something and then you might appear on our screens. Can you just unmute and say something? Okay, she's here, so I don't know. Do we have any questions? I guess I had a question, if we are able to. Is she okay, it seems like maybe it's an issue on your side. Oh, she seems to have gone now. Give her a second. Oh, yeah, we can hear you now. Can you say something again? I don't know. The sound is not very good. But anyway, my question was going to be, have you considered looking at these wave events and kind of conditioning on like antecedent land surface conditions, whether that matters at all or explains any variance of how hot and humid the heat waves get associated with these waves? Yeah, okay, I think we're it's a little muffled here in the room, so but thanks for your talk, and we'll move on to the next speaker. That's Patrick Martineau, who's in person. Oh no, he's.
My name is Patrick Martineau. I am a researcher at the Application Laboratory of Jamstec. In this presentation, I'm going to discuss the influence of ENSO on summertime high-frequency variability and the frequency of heat waves affecting South Africa. It has been documented that Southern Africa's intra-seasonal variability is modulated by ENSO. For instance, weather systems responsible for this variability, such as cold fronts, cutoff lows, and tropical temperate troughs, are all found to be more frequent during La Niña conditions. These studies, however, have defined these weather events based on absolute fields such as geopotential height, mean sea level pressure, and temperature. Therefore, the impact of ENSO on subweekly variability that is often associated with storm tracks remains uncertain. And studying the influence of ENSO on regions vulnerable to weather extremes, such as Southern Africa, is motivated by the potential to predict ENSO seasons ahead. From a zonal mean perspective, ENSO has broad impacts on the circulation over the Southern Hemisphere. This figure from Leroux and Thompson shows that during La Nina in austral summer, there is a weakening of the westerlies where South Africa is located. This is accompanied as expected by thermal relationship with a weakening of the temperature gradient, with cold anomalies over the equator and warm anomalies over the mid-latitudes, which correspond to a poleward shift of the region of maximum baroclinicity. In contrast to summer, the impact is negligible in wintertime. This reduction in baroclinicity in austral summer seems to be in contradiction with previous studies that have documented more frequent weather systems during La Nina conditions. To elucidate ENSO's impact on temperature variability, we analyze atmospheric energetics. We are focusing on eddy available potential energy, which is a function of high frequency temperature variance that is extracted here using a 10-day high-pass filter. There are many sources and sinks of eddy available potential energy, but for this analysis, we focus on the leading source, which is baroclinic energy conversion. It is achieved by eddy heat fluxes that are against a seasonal mean basic state temperature gradient. Here we express energy conversion as the efficiency by dividing the column integrated sources by the total energy of high frequency eddies. First, we are going to have a look at ENSO's teleconnection with Southern Africa. For this, we use a composite difference based on the Niño 4 index, which captures central equatorial Pacific variability. We chose this index because it is most strongly correlated with eddy available potential energy over Southern Africa. We observe, as expected, El Niño's signature over the Pacific sector in the sea surface temperature field. Concerning the atmospheric circulation, we find positive geopotential height anomalies over Antarctica, as well as over the subtropics, and a belt of negative anomalies in the mid-latitudes. It shares some similarity with the southern annular mode, although it is less zonally symmetric and has comparatively greater impact on geopotential height in the lower latitudes. Over Southern Africa, an intensification of westerlies is expected from the amplification of the climatological geopotential height gradient. Next, we are going to look at how this teleconnection impacts eddy available potential energy over Southern Africa. We find that during El Niño's condition, eddy available potential energy is enhanced in the mid-latitudes and impacts the southern coast of South Africa. Explaining the enhanced eddy available potential energy, we find evidence for enhanced efficiency of baroclinic energy conversion locally over Southern Africa, but also over the South Atlantic sector. This region of enhanced eddy available potential energy is in fact located over the trajectory of high-frequency eddies affecting Southern Africa. But this trajectory is identified using one-point regression analysis with respect to a reference to potential high time series over Southern Africa. We see that this typical eddy structure passes over the region of enhanced energy conversion and then affects Southern Africa via its equatorward flank. Looking into the factors modulating baroclinic energy conversion in more details, we find that the correlation between V prime and T prime over the Atlantic sector, as shown with the dashed green lines, is more negative than usual during El Niño condition. And that suggests that the structure of high-frequency eddies is more adequate for the poleward transport of heat, and thus the conversion of energy from the mean flow. So how does this impact on high-frequency variability affect the frequency of weather extremes? To illustrate this, we show the probability distribution of surface temperature over 4 reference locations over South Africa for El Nino and La Nina conditions separately. We observe, especially over the east, an increase in the frequency of warm extremes. This is explained in part by a shift in the median value towards warmer temperatures, but also by a broadening of the distribution, which is clearly observed when we adjust the true distributions to have the same median. The take-home message is that El Nino is associated with enhanced summertime high-frequency temperature variability over Southern Africa. The teleconnection of ENSO with Southern Africa shares similarities with the Southern enemy mode, but has a comparatively larger impact on South African weather. The enhanced high-frequency temperature variability is explained by enhanced biogenic energy conversion efficiency that is concomitant with an amplification of the westerlies or enhanced bioclinicity over the Southern Atlantic. The enhanced high-frequency temperature variance is associated with warmer seasonal mean temperatures, which together lead to more frequent warm extremes. The impact is limited to austral summer, and it is opposite to what studies defining weather events with absolute fields suggest. So this concludes my talk. Thank you for your attention, and I look forward to hearing your questions and comments. Thank you.
Thanks. Patrick, are you there on the Zoom?
Yeah, can you hear me?
Yep. Do we have any questions? Questions online? I guess I was wondering if you thought about whether what's going on in the Indian Ocean also modulates what you see in South Africa.
That's a very good question. So actually, we kind of did investigate, let's say, the dominant mode of the available potential energy over South Africa, and have removed from it the ENSO signal. And when looking at this impact without ENSO, we find very, very little correlation with sea surface temperature all around the Southern Hemisphere. So it really appears that ENSO almost has the sole impact on South African weather as a mode of coupled ocean atmosphere variability. So that all the rest of the variability from year to year is due to internal processes to the atmosphere.
Okay, thanks. Did you have another question? Oh, okay. There was okay. All right. Well, thanks a lot for joining. And we'll move to the next speaker, which is in person. And that's Rich Neal. Sticking with the ENSO theme, the Pacific North American circulation sensitivity to tropical divergence and vertical diabatic processes during ENSO.
All right, thanks, Isla. So this will be a summary of a paper and a little bit beyond the paper. It's work with University of Hawaii. And I think the key thing is part of the model diagnostic task force. And so this is an effort to integrate diagnostics that can inform model development. I'm going to jump straight in. And so what we're concerned about is we're looking at a PNA pattern, Pacific North American pattern. So this top figure here emanates from the tropical Pacific. This is ENSO anomalies, El Nino anomalies. I want to contrast that with AMIP simulations with the NCAR model. So these are prescribed SST, observed SST. And we've seen that if we look at the bottom left there, that's a previous incarnation, our CMIP5 incarnation of the atmosphere model. There's kind of a really weak propagation along that Rossby wave radiation pathway there through to North America. Where quite nicely, our most recent incarnation, CMIP6, has a much more robust pattern, and it's a little bit stronger than observations. So the question is, how can we understand that? And one way is kind of an established way is through the Rossby wave source. So on the left there, we have our observed picture there, and the bottom there is the source terms for the Rossby wave source, which is the barotropic single lobe vorticity equation. And if you the main contributions to that are the first two terms, which is a vortex stretching term based on the divergence, and then an advection of vorticity, which is based on the divergent flow impinging along the vorticity gradient. So if we look at that top right picture, there's a few variables here, but Precipitation is in the colors, and of course, ENSO is higher precip in the Central Pacific, reduced precip in the Western Pacific. So those two boxes I want you to keep in mind, the blue and green. I'll talk about those later. But in the Northern Central Pacific, there's a clear maximum in the Rossby wave source. So in observations, there is this generation of the rotational flow based on this Rossby wave source. And there's a lot more information about this in the paper. So can we see correlations with improvements in the PNA pattern? We can. So these two figures are kind of a repeat of previously. It was on the previous slide. In that Central Pacific region there, on CAM5, there is some increase. There's some local maximum in Rossby wave source, but in CAM6, it is much more robust. So you can have this correlation between Rossby wave source and that PNA pattern. If you look on the left, that's a little bit complicated, but essentially this is the evolution of the PNA on the y-axis and the Rossby wave source to see how they're related in a selection of CMIP models, but they're AMIP. And the 5s essentially are CMIP 5 versions, are older versions. And the 6s are more recent versions. So we can see for the most part, we're going from the 5s to the 6s over time for individual models, and that's an improvement. It's an increase in the PNA strength and an increase in the Rossby wave source strength. For the remainder of this talk, I want to talk a little bit more about the divergence from the tropical component. How can we understand that? With the ultimate aim of understanding the tropical physics that result in this divergence pattern. So what I'm showing here, I want you to remember back, this is the West Pacific piece of that anomaly pattern. And now we're looking at the vertical distribution of divergence. And it's interesting, we look at different reanalysis products here, and we're looking at climatology on the left, which is obviously in the West Pacific, very strong divergence, upper level, very weak divergence, pretty strong convergence in the lower level. And then the anomalous signal on the right-hand side. So for the West Pacific, the analyses are in good agreement. There is some variation in that typical level. So what I showed previously was 200 millibars. So where that line is there. But for these particular analyses, the line of the kind of level of maximum divergence is actually higher. And it's actually a little bit different between El Nino anomalies and climatology. So just to give you a sense of, if you're picking a typical divergence level, there's things to think about in terms of what that is based on the anomalies and the climatology. That's the West Pacific. We look at the East Pacific, it's surprisingly different. So there's disagreement amongst, but particularly in climatology amongst the reanalyses. So yeah, they get the divergent level, the maximum, they get the upper level divergent level pretty good, but there are very significant disagreements, particularly with MERA 2. And there's also this multiple modal structure, if you like. It's not a single deep mode in the vertical. So essentially climatology is quite a bit of disagreement, but their response to the anomalies, it is the same, obviously SST, is much more robust. Now, I think it's interesting, again, you know, the emphasis on how typical is that 200 millibar divergence level? How does that describe the upper level divergence field for the purposes of this Rossby wave source equation? And the answer to that is, if you look at the level here, I'm plotting the mean and the top one DJF level of divergence from era 5 in this case, and then the El Nino anomalous divergence. You know, and I have done, and you can look at these for a long time. They're really interesting. And so there is no typical per se within the like Indo-Pacific region maximum divergence level. It goes from as high as 100 millibars on the it's kind of in the middle there, Pacific right here, and then into the Indian Ocean, you know, it's much lower, around 250 millibars. So it's hard to imagine there is a typical divergent flow there. One of the regions with the most disagreement, actually more than what I showed, is in the Central Pacific ITCZ. And there are really challenges in models, you know, essentially it's a lot of model for era 5 and all the analyses in the Central Pacific, and they actually disagree quite significantly in terms of the upper level divergence. So last two, moving on to the models to try and understand CAM5, CAM6 evolution. And here I'm kind of doing the same thing again. Sadly, I flipped them, sorry. So on the right-hand side is the climatological divergent profile from a selection of models that, to a certain extent, not linearly, but they traverse from CAM6 back to CAM5. So in principle, if it was linear, you'd say I'd be able to identify the cause of this difference in divergence. Does that play a role into the Rossby wave source changes? And in the West Pacific, you know, there are a lot of pretty significant changes associated with boundary layer, convection, et cetera. And we can see that they're pretty robust. The West Pacific is a very strongly forced region, deep convection, and they're kind of, you know, there are issues there you can see in the lower troposphere near the surface, but for the most part, they agree. And the left-hand side is back in this Central Pacific region, where the SST anomalies, the convective anomalies in observations exist. And, you know, quite clearly the most uncertain region is exactly in this divergent region, which is, you know, 300 to 100 millibars. So it represents, you know, a challenge, and this is the next phase of trying to, again, relate the vertical processes in the model to the upper level divergence. My last plot just illustrates this from respect to the temperature tendency, the diabatic temperature tendencies of the moist processes from all those simulations. And, you know, there's if you just flip back, mustard and purple on the right-hand side, they have the greatest upper level divergence. That makes sense. But a lot of the, in the East Pacific on the left here, a lot of the detail is associated with what's happening way up between 250 and 100 millibars. And then, and so, again, that links in with this divergent flow pattern, the divergent source term, and trying to understand how that will impact the Rossby wave source. So that's the kind of extension to the paper we're working on. So, quick summary. PNA pattern is improved quite significantly in CAM6 during El Nino, and it seems correlated to the Rossby wave source strength. There are a number of things I didn't talk about here, but away from the tropics, there are aspects of the jet curvature and Rossby wave number limitations that have resulted in the improvements. And then the next three are just what I talked about briefly, trying to understand vertical processes and divergence. So finally, I just want to mention that on the bottom here, the diagnostics, including the first part and hopefully the second part, are available through this MDTF framework. Okay, thank you.
Thank you. Do we have any questions for Rich?
Maybe I can add
Yes.
the.
Go ahead. We know that diabatic processes move air from one isentropic level to another.
Right.
So I was wondering, can we do this analysis on isentropic levels? And you did most of the analysis on isobaric levels.
Yeah.
And what could be the advantage and disadvantages of using that?
Of doing it on isotropic levels. Sorry, I missed that. Sorry.
Yeah, the last. I want to ask, what are the advantages and disadvantages of using isobaric levels?
You know, it's typical framework. It's good in the tropics, of course. It's hard to know at this point. You know, I've been focusing mostly on the individual process representations rather than thinking about what you just mentioned. Yeah, it's I'd have to think about it quite a bit more, actually. Yeah, thanks. Sorry.
Thank you. So we'll move on to the next speaker. That's Chen-Shuo Fan on the weakening of the tropical circulation caused by lifting of the tropopause height.
Okay. Morning, everyone. My name is Chen-Shuo Fan, and I'm a PhD student at Monash Universities in Australia. Today, I'm going to share one of our research results, which shows the weakening of the tropical circulation. It's caused by the lifting of the tropopause height. And like the sketch shown here, we find the tropical circulation in general is weakening under global warming, and it is due to the rising tropopause height. And this work is done by me and my supervisor, Professor Dima Damjit. So in this talk, firstly, I will introduce our research motivations about the understanding the tropical circulation changes under global warming. And then I'll introduce an important research tool for this study, which is based on the moist static energy balance framework. After that, I will explain one of our research findings about what caused the weakening of tropical circulation. So our research motivations comes from the precipitation change under global warming. Like the plot here, it shows the projections of precipitation changes under global warming by the most contemporary CMIP6 models. And the green color here indicate more rainfall in the futures. Brown color indicate less rainfall in the futures. The hatch areas means low agreement among 33 CMIP6 models. And according to Held and Southern's work in 2006, under global warming, they indicate the precipitations only increase 2 to 3% per K, while the moisture increase 7% per K. Thus, it implies a weakening circulation, which reduce the transportations of moisture for precipitation. However, there is a strong regional difference, especially over the tropical regions, which cannot be simply related to the weakening circulation. In addition, the large uncertain area here also points out our lack of understanding of future climate. Therefore, in this research, we aim to understand the physical process that cause the tropical circulation changes under warming scenarios. And we will especially focus on the vertical motion perspective. So in this study, we developed a simple diagnostic model for large-scale circulation based on the moist static energy balance framework, or we call the MSEB models. And the MSE combines the air partial enthalpy, latent energy, and potential energy, and which is quite similar to the equivalent potential temperature. So by looking at the equation here, red part represent the net energy heat flux into the air columns, and which is the function of short wave, long wave radiations and latent heat sensible heat flux. The blue part represent the MIC advections, which includes the temperature and moisture advection. The angle bracket here means the troposphere's whole troposphere's integration, and PT here is tropopause height. The green part represent the atmospheric stability in relation to the vertical MIC gradient and weighting by the capital omega, which is the barocaninic mode. So the top heavy shape here basically mimics the deep convection structures in the tropical regions. And in the following analysis, we will rearrange the equation here and create abbreviations as shown on the right-hand side. So F is net energy heat flux, A is MIC advections, and M is atmospheric stability. So for our analysis, it's based on 23 CMIP models dataset. We take historic climate from 1970 to 1999 as control scenario. And we take SSP5 radiative forcing data from 2070 to 2099 as warming scenarios. Our research regions is over the tropical oceans. So the plot here shows the CMIP ensemble mean vertical velocity at 500 hectopascal. And all the negative value and positive values represent the upward motions and downward motions, respectively. So the first row here shows the mean circulation under historic climate. And here shows the circulation response from warming scenarios minus historic climate. And the second row here shows the corresponding estimations from the MSV model. So for the first columns, the pattern correlation is 0.74. And for the second column here, the pattern correlation is 0.68. And this result indicate the MSV models has capability to capture the mean circulation and circulation's response signals quite well. And it is a useful tool for our study. So in terms of the global tropical perspective, we compute the Lu mean square ratio of circulation response to mean circulations. So as shown on the right figures, the axis is a time series, y-axis is a Lu mean square ratio. The positive values means the circulation is strengthened, and negative values means the circulation is weakening. The blue and red lines means the result based on the CMIT-6 ensemble mean and corresponding MSB estimations. And here, these results indicate the MSB models can simulate the weakening circulation signals, and it weakens by about 10% over 21st century. So in order to understand what caused the weakening circulation, we apply the sensitivity analysis to quantify the contributions of each turn in the MSEB models. So there are three main components in the MSEB models. One is net energy heat flux, and another one is advections, and the last one is atmospheric stability. For example, the sensitivity of circulation response to net energy heat flux can be described as the estimated vertical velocities with components from historical climate, except the net energy heat flux turned from warming scenario, and minus the estimated vertical velocities with all components from historic climate. And on this bar chart here, the y-axis is a Lu mean square ratio. The first bar shows the CMIT-6 ensemble mean results, and it indicates the circulation weakening by about 10% under warming scenarios. For the second bar here, the MSB model also shows the similar result. For the rest of three bars, they are the sensitivity analysis of each turn of the MSB models. And it indicates, it shows the weakening circulations is due to the increased atmospheric stabilities under warming scenario, which reduce the strength of circulation. So regarding the MSB framework, the change of atmospheric stabilities can be decomposed into the contributions from baroclinical mode and vertical MSC gradient. So here's the figure shows the baroclinical mode and vertical MSC gradient and cumulative stabilities from surface to the tropopause height. And the blue line shows the result based on historic climate, and red line shows the result based on the warming scenarios. And we find out there is a shift upward shift baroclinical mode, which weights more the stable air mass than the unstable air mass under warming scenarios, and further increasing the atmospheric stabilities, like the red by comparing the blue line and red line here. So in the MSB models, the change of baroclinical mode can be further decomposed into contributions from temperature profiles and tropopause height. And we found the change of tropopause height plays the most important role to shift upward the baroclinical mode. So based on the CMIT-6 ensemble mean results, it shows the tropopause height lifting under warming scenarios. According to the previous results, we are here to provide a conceptual synthesis. So first, the CO2 forcing lifts the tropopause, and this will further higher up, shift the baroclinical mode higher up. And then it will make the upper level stable air mass become more important for the air current stabilities. In the end, the circulation will stretch up and become weaker due to the stable air column. Summary, the MSB model is a useful concept to analyze the large-scale tropical circulations. And According to our results, the main driver of general weakening tropical circulations is due to the lifting of the tropopause height. Thank you for your attention. I'm happy to take any questions and feedback.
Thanks very much. We're a little over time, so I think we're not going to take
Sorry.
any questions, but feel free to reach out after the session ends. Thank you. We'll move on to the next speaker. That's Sisam Shrestha. Talking about weakening of the tropical circulation in CMIP6 for different sea surface temperature warming patterns.
Good afternoon, everyone. Welcome to my talk. Today, I'll be talking about the weakening of large-scale circulations in CMIP6 for different SST warming patterns. We'll first begin with some background information on how we expect large-scale circulations to behave in a warming world. Studies like held in Soda in 2006 provide a hydrological constraint on the weakening of large-scale circulations, which can be understood using this relation between precipitation, convective mass flux, and near surface humidity. So as you can see from the scatter plot above, precipitation increases at a rate of 2% per Kelvin. Surface humidity scales with Clausius-Clapeyron around 7% per Kelvin. And this differential rate of increase between the two variables leaves us with a negative trend in convective mass flux in a warming world. Investigating the change in convective mass flux for the A1B emission scenario, we see an overall weakening pattern in large-scale circulation across the model, and this weakening primarily manifests as a reduction in the zonally asymmetric component of the circulation. If we turn our focus in the tropical Pacific region, we see that this weakening in the asymmetric component is primarily manifested as a weakening of the Pacific Walker circulation, which here can be seen as an increase in sea level pressure in the Western Pacific and a decrease in sea level pressure in the Eastern Pacific. However, recent analysis using observations and reanalysis dataset indicate a strengthening of the Pacific Walker circulation, as can be seen in this diagram from Zhao and Allen, which shows an increase in the tropical Pacific sea level pressure gradient between the East and the West Pacific. Also, if we look at the SST pattern for this period of 1979 to 2014, we see that the observations show a completely different pattern compared to the coupled models. So in this case, we look at the atmospheric models from CMIP6, which has SSTs based prescribed in observations. The AMIP simulation show a La Nina-like pattern with cooling in the East Pacific and warming in the West Pacific, consistent with the idea of a strengthening of the Pacific Walker circulation, whereas the coupled models, that is the historical simulation, show an overall warming for this period. A similar difference can be seen between the simulation for the omega 500 trend, where the AMIP shows a overall strengthening of the Pacific Walker circulation with strengthening of convection in the West Pacific and a strengthening of subsidence in the East Pacific, whereas the historical ensemble mean shows an overall weakening of both the convection and the subsidence region. Now, this difference in what we've seen in the recent decades for circulation versus how we expected circulation to behave like in a warming world poses some very important questions. So in today's presentation, using two sets of CMIP6 experiments, the AMIP with observed SSTs and the historical coupled runs, we will try to explain the following questions, which is, does this weakening with warming still hold true? Can mean circulation weaken despite a strengthening of Walker circulation? And what do observations indicate about the behavior of large-scale circulations in this period? Due to time constraint, I'll only be going over the results derived from changes in convective mass flux. However, similar conclusions can be drawn from other strength indices used to quantify large-scale circulations for this period. We begin our analysis by looking at the historical ensemble for 1979 to 2014. As you can see, all the models that are represented by the thin blue lines show an overall weakening pattern in large-scale circulation, and the historical ensemble mean, represented by the bold blue line, estimates a weakening at around negative 0.98% per decade. Next, we'll look at the AMIP simulation, which from earlier showed a completely different pattern compared to the historical ensemble. There you go. Even in the AMIP, despite a different SST pattern, we still see that weakening of large-scale circulation with the ensemble mean and channel variability correlated with the ENSO variability, and the ensemble mean weakening at a magnitude of around negative 0.64% per decade. So despite different SST patterns, both these simulations show an overall weakening of large-scale circulations. We'll now analyze how the observations show large-scale circulation trend for the common period of 1988 to 2014. The red line here shows change in global convective mass flux for observation. As you can see, the observations too show a weakening of convective mass flux at around negative 0.52% per decade, with the statistical uncertainty at the 95% confidence interval. The weakening, although much smaller in magnitude than the historical ensemble mean, is closer to that estimated from the AMIP ensemble mean at around negative 0.65% per decade. Now, the issue here is that our observation data runs all the way from 1988 to 2014. The CMIP6 historical and the AMIP simulations stop at 2014 for most of the models. We cannot extend the AMIP since it has SSTs based prescribed on observation, but we can integrate SSP 585 scenario MIPS to extend the historical data set. So this figure here shows the extended time period for our global average convective mass flux. At this point, we also integrate the CSM2 large ensemble, which had the data necessary for it to be extended to the year 2021. So as you can see from this figure, both observations and models, that is the historical and the CSM2 large ensemble, show an overall weakening of large-scale circulation, with the observation, for the most part, lying within that large ensemble range. Also in this figure is the PI control ensemble mean, which shows a near zero decadal trend for this period, suggesting that internal variability alone cannot explain this weakening that we've witnessed for this 1988 to 2021 period. And lastly, we look at the temperature sensitivity of this weakening at both the global and the tropical scale. As you can see, for the observations and the models, both of these data sets simulate a weakening of the large-scale circulation per Kelvin increase in global temperatures, with the global weakening estimated by the observations at around negative 4.5% per Kelvin, which is similar to that value derived from the hydrological constraint that I talked about in the first slide. For both the cases, the CSM2 large ensemble mean, which is shown by the green vertical line, has a higher sensitivity compared to both observation and the historical ensemble. So just to wrap things up here, does this weakening with warming still hold true? Well, yes, it does, according to the robust weakening signal that we saw in both historical and AMIP simulations. And yes, the AMIP simulations have a weakening of mean circulations, even with strengthening of Walker circulation, suggesting that mean weakening can take place despite the strengthening of Walker circulation. And also for this period, observations too suggest a weakening that is consistent with model projections. And as we saw from the black PI control line, internal variability alone cannot explain this weakening for this 1988 to 2021 period. And that was my talk. I'd like to thank the NASA Finance Grant for supporting my work. And thank you all so much for attending my talk today. If you have any questions, comments, or suggestions, I'd be happy to take them.
Thank you. Are there any questions? Yep. Come on.
Thank you for a very nice talk. Just one quick clarification question. What was the observed estimate of the convective mass flux?
I'm sorry,
maybe I missed it.
can you repeat that question?
I think it was what data set was used as the observed mass flux.
Okay, so we estimated our observed mass flux using the differential rate between precipitation and surface humidity. So for precipitation, we used the GPCP dataset, and for surface humidity, we derived it using the SSMI dataset for total column water vapor.
So using a monthly or daily time span?
We used the monthly resolution datasets.
Thanks.
There was one other question somewhere. I guess I have a very quick comment, which is that there is an AMIP ensemble with CSM2 that goes to 2021, which might be an
Oh, okay, yeah,
additional
yes,
useful
I will look in. Thank you.
All right, thank you. So this is our final speaker now, Fayaz Ahmed, talking about the physics of ITCZ narrowing under global warming captured by a simple process model.
All right, thank you. And this is work looking at the physics of ITCZ narrowing using a somewhat arguably too simple a model, but also useful, as I'll show. And yeah, acknowledging funding from DOE as well as my collaborators. Okay, so the ITCZ defined as regions of the tropics with time mean ascent, which also overlaps with the tropical regions with time mean heavy precipitation, as shown here on the top left. And under global warming, we know largely thanks to experiments with complex climate models using increased CO2 or SST, that the ITCZ narrows and intensifies. And by narrows, I mean areas occupying time mean ascent shrink, and the precipitation within these areas increases in intensity. And also the circulation that accompanies these changes, including the strong ascent within the ITCZ strengthens, and the descent within the subsiding zones weakens. So yeah, so a lot of robust features that we know from climate model experiments. And then the next question is, why do we see this? Okay, so there's a nice framework put forward by Bohn and Schneider back in 2016 that introduces this atmospheric energetic perspective on this problem. And essentially what they say is take the tropics, locate the boundary where you have the ascent that separate the tropics into an ascent zone and a descent zone, and write the atmospheric energy budget. So the dry static energy and the moist static energy budget separately for each of these two zones. That gives you an implicit equation for the fractional area of the ITCZ. And you can do a perturbation set of analysis for this implicit equation and argue that under global warming, the energy partitioning between the ascent and descent zones changes, and the fractional area of the ITC sort of has to change to compensate. So our question was to sort of ask if we can derive an explicit solution for the fractional area of the ITCZ. And what I mean by that is, can we represent the fractional area of the ITCZ as a function of current climate properties, most obviously including the surface temperature? And the short answer is we can, but we have to simplify the problem considerably, starting with zonal and meridional symmetry. So no variance in the longitudinal direction, and profiles are mirror images across the equator. All right, and then we also exploit this relationship between precipitation and water vapor in the tropics. So we assume that a single value of water vapor separates the tropics into a moist precipitating zone and a dry non-precipitating zone. And this you can see from just distributions of water vapor and conditionally average precip, but you can also see it in just these time mean maps, like the one on the top right. So here is a precipitation contour from GPCP, and the white line is a single valued contour of column water vapor from ERA5. And you can see that this contour nearly bounds the regions of the tropics, what you would intuitively think of as the ITCZ. So which means in our framework, we use the surface temperature profile to first derive a column water vapor profile, like shown here in orange, from which we then derive a precipitation profile, like shown here in blue. And then we can measure the width of the precipitation profile, which I'm denoting as Y sub P in this framework. And once you know Y sub P, you can also derive the ITCZ area. And a couple of other remarks. Now, the model deals with the fractional coordinates, so there's no absolute distances. So you have y equals 0 and y equals plus minus 0.5 at either ends of the domain. And also there's no explicit rotation. So this sort of falls in the family of mock overturning circulation class of models, which people have used to look at Walker and Hadley overturning circulations in the past. Okay, so, all right, so we have the setup, we now need some physics. So we tried to put as much physics as we could into the model without sacrificing tractability. So we have parameterizations for clear sky, cloudy sky radiation, convection, and poleward moisture export. And so I won't go into the details of these parameterization schemes, but I'll just say that these are highly idealized representations of complex physics, but we sort of try to appeal to empiricism wherever possible using climate model data mostly. And all of these different processes have either a direct or an indirect dependence on the column water vapor and surface temperature. All right, with that, we can go ahead and write down the atmospheric energy budget at a single point in the domain. This is y equal to 0. This is our nominal equator, nominal because there's no rotation. And this is the atmospheric energy budget shown in the blue box. So you can see it has terms like atmospheric heating, evaporation, and precipitation. And on the left-hand side, you have this parameter m naught, which is gross moist stability, which is sort of a notorious parameter in theories of tropical dynamics, which we heard about a couple of talks prior to this. And simply put, this is the efficiency with which convection exports moist static energy out of convecting columns. And some foreshadowing here, like this turns out to be a critical parameter in this model and also for explaining intermodal spread. And into this expression, we can throw in our parameterizations for convection and radiation that I showed before, as well as the functional forms for surface temperature and column water vapor. And we can derive this quadratic for where the unknown is the y sub p, which we call it the width of the precipitating moist region, or the fractional width. And the coefficients of these quadratic are dependent on the various parameterizations. And if you solve this quadratic, you get an explicit expression for the fractional width of the ITCZ. So let's see how this model does, with some simple experiments. So on the left are a series of surface temperature profiles, and each profile differs from its neighbor by 1 Kelvin. So this is a uniform warming experiment. And the black here is sort of the closest you get to a current climate surface temperature profile. And in the middle panel are a series of precipitation profiles. And each precipitation profile is an explicit solution that is derived as a function of the corresponding surface temperature profiles. The correspondence is given by the color. And as you can see, as your domain warms uniformly, your precipitation profile narrows and intensifies. And we can also derive expressions for the strength of the ascent in the precipitating zone, the strength of the descent in the non-precipitating zone, and how these properties change with climate are shown in the right panel. And we see that the ascent gets stronger under warming and the descent strength gets weaker. So at the leading order, these properties are qualitatively similar to what you'd expect from a more complex climate model experiment. So we think we've isolated the physics. And then we also asked, despite being an idealized framework, can we use this to explain some aspects of, say, the intermodal spread? And so we took a set of AMIP models, and for each AMIP model, we estimated physics parameters, and we sort of fed those parameters into the simple model, and we were able to get a prediction for the ascent area change over the historical period in units of percent per Kelvin. And we were also able to directly measure the ascent area change using, say, vertical velocity fields from the AMIP model. And the correlation between these two, I know, is far from 1, but it's also far from 0. So the simple model, despite being idealized, has modest skill in explaining some aspects of the AMIP intermodal spread. And we did some further digging and found that the gross moist stability, which I alluded to earlier, is a large source of the spread. So no surprises there. Yeah. Anyway, so that concludes my talk. So we built a simple model, and that essentially demonstrates that the ITCZ contraction problem is an atmospheric problem once the surface forcing. And among AMIP models, the gross moist stability is a large source of spread. I'll stop there. Thanks.
Thanks. Yep.
In terms of what controls the actual strength of the ITCZ, a lot of it is a polar equator temperature gradient also. I mean, the way I understand it, you kind of just elevate it systematically everywhere. And I wonder whether you've tried, is it possible within the framework?
Yeah, it is possible
to,
to.
because if you have sharper on the equator, then you're gonna at least spin up and maybe narrow or not or thicken the edge.
Yeah, so you can make the SST profiles flatter or sharper.
Right.
And that also has an impact on the the ITCZ properties. But
do you get a better fit? Do you know?
Okay, yeah. So it's AMIP. So we assume the surface temperature meridional gradient does not change. That's one of the reasons we used.
Yeah.
That's why we did not use because yeah. Thanks.
Yep.
Thanks for the talk, Faz. Great talk. Can you comment on aspects of how, if you incorporate seasonality, how this may change? I'm wondering if there's any type of asymmetry, or is it going to be narrowed throughout as it shifts from hemisphere to hemisphere?
Yeah, thanks. So the physics is somewhat constant. So the seasonality has to enter to the background state, which in this case is, again, the surface temperature profile. That's the only control that's the only external control. So yeah, if that would change, then seasonality would be reflected. But you could also incorporate zonal asymmetry into the problem, and that would also have an impact. But yeah, qualitatively similar.
Oh, yep. One more quick question.
Hi, thanks very much for this model. You've compared how the ascent area changes. I'm wondering if you've compared how the descent zones have changed in your model compared to the CNIPS. Thanks.
It's a good question. So in this model, it's the ascent area is fractional. So the descent zone is just 1 minus the ascent area, but I have not seen how that compares with the actual AMIP model, because in climate models, you can also have an expansion of the Hadley cell, which is not in this model explicitly. So, but yeah, good suggestion. Thanks.
Okay, thank you. So that concludes this session. Please join us again after lunch. And thanks all the speakers for keeping on time and for great talks.